So today I'm going to tell you about dynamics of spin glasses above freezing temperature. First part will be related to theory of mean field spin glass dynamics, where everything can be calculated explicitly. Then in the second part I will show you how it looks like in real experiments and in Monte Carlo experiments. And finally, I'm going to discuss some model of diffusion which was invented in order to provide some theory for the behavior of real dynamics of real spin glasses, which is quite different from what we can derive in the mean field level, as you will see. So let us start. Basically, I will follow this paper by Chaim Sempolinsky and Annette Zepelius, where they start from the Hamiltonian, Edwards Anderson Hamiltonian, which is, we already have seen it, sum of all pairs of spins with some random couplings, J, Ij, Ising spins, plus minus 1, and distribution of each probability distribution for each coupling is a product of probability distributions on each link, which is Gaussian. With Gaussian, could in principle have some non-zero average, but basically I will consider a situation with J naught equal 1. Now, first question is how we are going to describe dynamics. Dynamics for discrete variables should be also some discrete metropolis type dynamics. And it is possible to start with from such discrete formulation, but in this paper and in many others, we used another approach, just saying that let us consider, instead of discrete variables, some soft spin version, which means simply that you consider sigma as a continuous variable which has such a kind of local energy as function of this sigma I, and with minima at plus and minus 1. As of course it is a different model, but it is quite possible to show that critical behavior for both types of models, hard spin and soft spin, that critical behavior near transition temperature is the same, no difference. This is a Hamiltonian. You see that here this term with delta function is a quadratic in sigma, and this is 4 order in sigma, which is an external field. Then dynamics can be written in the simplest way as a dissipative Langevin dynamics, where time derivative of any of these spins sigma is a force, generalized force, which is a derivative of the Hamiltonian over sigma, corresponding sigma I. Plus some random noise, of course, since we consider a system at a non-zero temperature. And according to fluctuation dissipation theorem in this classical limit, correlation function of random noise has a coefficient related to the dissipative coefficient gamma naught, which stays on the left-hand side. So this is a relation between fluctuations and dissipation.
Considering this model with continuous spin is possible only in a theory which have a definite midfield limit, or is always?
No, it is. It does not depend on if it is mean field limit or not. You can do it in finite range system as well. The difference, I will explain what is the difference on the next stage. So here we come to this system of nonlinear equations with first order derivative over time with randomness which is sitting in Jij. And what we need to calculate is a spin correlation function and a linear response function. These two functions are related by fluctuation dissipation theorem, which in a classical limit reads just like this. Then also you know that there is a relation between imaginary and real part of response function, which is shown here. Right? It is just a consequence of retard nature of response function. Response function at J at t less than 0 is 0 due to causality. So using this general fluctuation dissipation theorem and this Cullen-Welton relation, we can see that in the classical limit there is a very simple relation that correlation function at coinciding time 0, is just equal to the response function at zero frequency. And we will use this relation later on.
Are we considering the case where the ATH works so at equilibrium we have eigenstate thermalization hypothesis?
This is classical system. And moreover, we are, even if it would be quantum, we are above transition temperature. So everything is ergodic. So fluctuation dissipation theorem works in its classical form. But our equation is a system of many equations for sigma I, and these equations are nonlinear. Looks rather complicated. Nevertheless, there is a trick how to deal with such equations. And it was developed long ago in this paper site here, Martin Sigierose and De Dominicis. The trick is the following. We want to, eventually, find our correlation and response function averaging over solution of this system of equation. Now, let us write down a generating functional, which the idea of this generating functional is that instead of solving with nonlinear equations, which is impossible explicitly, let us write down a delta function. I will write a simplified form of the equation. Let us, yes, and here some psi of t. Instead of averaging over solution of equation, let us average functional which is made out of delta function of equation itself. Of course, then we should also take into account determinant. This determinant will take care of the fact that this expression is non-linear, non-trivial function of phi. Okay. Now, we also need to average, so let us write down it as SF integral over phi, functional integral over trajectories, phi of t, and also trajectories of noise. How to average over noise, we know. It is minus integral over time, psi square time over 4t gamma. So it is Gaussian distribution over noise, which corresponds to this delta function correlation, which I have shown before. As it is written, this expression is simply representation of unity. If we take this integral, we will get 1. But we want to have expression useful to calculate correlation functions. So we need to add here integral, the time, some L of time, phi of time. Then this will be a functional of the sources L, and by variation of this functional with over L, we will generate any correlation function of phi. This is general idea.
Phi itself does not depend on the noise.
It depends to the solution of the equation.
Yes, of course.
That
Phi is our, phi, which I wrote here, it is just sigma in these formulas. And psi is this. It is a noise in the Langevin equation. So this is exactly what is written here in the first line, apart from the fact that here it is also written not just directly delta function, but it was exponentiated. So we introduce additional variable sigma with hat in such a way that So integral sigma hat e I sigma hat, and then the expression which stays under delta function. And also we have two kind of sources, L coupled to sigma and L hat coupled to sigma hat. Now, here, L, this functional, it depends on sigma and sigma hat, and it contains all terms which come from, yes?
Why do we add the source field also for the sigma hat if it's
Because we want to calculate not only correlation function, but also response function. And the response function will be average of sigma hat, like this. Look, you see here with L, sigma and sigma hat. There is a term with H. With H, it should, I would need to have this H here in this generalized force. So, in order to get a average value of sigma at time t, I need to take a functional derivative over L of t, right? Good. Now, if I want susceptibility, so I need to vary this thing over h of t prime. Then variation of this h t prime, you see h is here, it is multiplied by sigma hat. So this variation is equivalent to calculation of average of sigma of t, sigma hat of t prime. Just identity. Now, apart from all these terms, we have additional v here, and this v is a result of calculation of the determinant. See here, we should account for the determinant. Actually, for when dynamic equation is so simple, it is just first derivative of our sigma is some function of sigma. It is easy to calculate this determinant. It is given by this expression. So we know it in the explicit form. But basically, we even don't need to work with it. What we need is to ensure that our functional is correctly normalized. So at zero source, this functional is equal to 1. And then, yes, this any correlation function of sigma and sigma hat is a functional derivative over sources, which is calculated when sources are put to 0. And the response function is non-zero when t is larger than t prime. There is no backward action in time. Now, the property of this functional that it is equal to 1 without, in the absence of sources is extremely important because it allows us to average over random parameters j, ij, which are here, immediately now. So let me emphasize, if I would deal with the usual equilibrium statistical mechanics, we can write down partition function in terms of functional integral over some fields. It will contain random parameters like j, j. And we cannot simply average partition function because what we need to average is a free energy. It is a logarithm of partition function. Because partition function itself is some functional of these random parameters, and to average it, it makes not much sense. The trick with this dynamic functional is that this functional is trivial in the absence of sources. So the averaging can be done directly. Averaging goes with this Gaussian weight. So this is the result. What you get after averaging over j's are terms of fourth order in sigma. And they coupled sigma I, sigma j, and sigma I, sigma j. Also here terms with it becomes a double integral over time because random parameters are time independent. Here, by writing this expression, we also use symmetry, that our matrix J is symmetrical. Good. Now we also have this L naught in the Lagrangian, the part which do not contain matrix element J. It stays the same. Good. Now our dynamic functional does not contain anything random, but it contains fourth order terms which are not so good to deal with. At this moment, it becomes crucial that we consider infinite range model. Because for infinite range model, where here this sum goes over all pairs I and j, we can decouple these four order terms by introducing Hubbard-Stratonovich fields, Q. This Q refers to site, in principle, it refers to site I and j. Also, there are four different fields, Q, and they all are matrix in a time space. So they depend on T and T prime. Here, the coupling between these Q fields and sigmas is given here. Yes?
Why does the same Q for sigma, for couples of sigma and sigma at
But they are different. You see, this is why there are four of them.
okay.
Q1 with sigma, Q2 is sigmas. Here there are sigma hat, and these have one hat and one without hat. Now, for if it would be a finite range system, I would need to deal with Q matrix field, which depends only on the point in space, but which would be quite difficult. but in the infinite range limit, there is no dependence of this subscript. It is sufficient to have just one matrix for all sides, which makes the problem much simpler. So
Is it the same as starting from Sherrington to Putney?
yes, it is just this. So here you see in L, in this effective Lagrangian, we have L naught and these terms bilinear in sigmas. Here it is basically the same. Now, actually, we don't need 4 different fields Q, because one of them must be 0 with Q2. Otherwise, if it would be not 0, we would get a violation of causality. If it would be not 0, then we will find that this average, which is response function, would be non-zero at wrong sequence of time. So, in fact, we have 2 independent Q fields here, and effective Lagrangian can be written in sorry, one thing I forgot to say. So what we will need is Q1, which is why this equality is written, because I mean that because of this large factor n here, due to infinite range model, I can use a saddle point approximation when I integrate over this Q T prime. So you see here this saddle point equation give me this set of identities. So Q1 is actually nothing but average correlation function, which is further is denoted as C of time. And with Q2 is 0, and Q3 and Q4 are response function, which is denoted as J.
And one question.
Yes.
The causality or the vanishing of this Q2 is something that we impose, or is something that comes naturally from the theory? If I do the calculation of sigma bar, I would get the 0 with the condition function.
Well, if you want to have a theory with causality, then you need to impose it. Okay. If you don't, then you can get something. So it is the choice just to use the causality as basic principle. So this is Lagrangian rewritten when we in the form where we have 2 functions of time, C correlation and J response function. When L naught is all this combination, And here, if we look here, the inverse, bare inverse green function is made out of the terms which are linear, bilinear in sigma hat and sigma. So it is this term which gives you I omega over gamma naught. Then it is this term stays here. But also I include here what comes from this average over J. Because here you see this sigma hat and sigma, which comes with the integration over J and of G full response function and J squared. So it is this term here. Now, noise effect, we had just white noise originally in our model, which was characterized by this delta function and gamma naught. But now we have modified noise because of this term. Sigma hat stays with a correlation function C. So effective noise contains bare term and this term with C.
What is the effect of this C that has been fully transformed is something that I lost?
Say it again.
The effective noise phi is coming from the psi.
From Xi, what was coming from the Xi is this.
Yes.
And the second term comes from here. Because this formally, this term in the functional is of the same form as this. You see here, sigma hat, sigma hat. But it is bilinear in this sigma hat.
What is phi? What does it mean effective noise?
It means, okay, this phi is what replaces original bare noise, which I denoted as Xi. Why it changes? It changes because of interaction between spins. We integrate in our dynamic functional, we integrate over couplings, J, J. It means we took into account that these spins interact. Each of them fluctuates. And because they interact, they modify also noise, which is applied to any of these spins. And this interaction is accounted for by this term. Now, here I write it J naught minus 1. So why J naught? Because actually my equation for sigma is nonlinear equation. It contains also these third order vertices, which will not be very important. Actually, this we will see, but they exist here. So J naught is a green function without account for this nonlinearity. But it will account for interaction, which comes from this term. So it is basically, diagrammatically, I can describe it like this. response function on a site I is bare response function, just this. Then I can hop. This link means J, coupling. So I can go to another site, spend some time here. It will be described by the full green function. When I go back, again full green function. So this combination is a graphical representation of this term. Okay, now what I want to find is the most important quantity which I need to find is a relaxation rate, which is given effective relaxation rate, which is given by this gamma minus 1, just a derivative of inverse response function over frequency. The function itself obeys a Dyson equation, usual Dyson equation. Then we differentiate this equation over omega and take into account relation which we discussed before. What we will get is this expression. And here it is a bare kinetic coefficient. Now let us make an assumption, which we will prove later on, that this derivative of self-energy over omega is some finite number in the limit of zero frequency. We will check it later. If so, then gamma minus 1 is given by such expression, which diverges when temperature is such that Tc is J multiplied by G function of zero frequency. Now, on first sight, we don't know what is this J of 0. We did not calculate it. But in fact, we know. As I told you before, we have a very important relation coming from causality and fluctuation dissipation theory. J at I equal to J, zero frequency, it is the same as correlation function of spins at the same site. And it is 1. Well, it is 1 in hard spin model, of course. So it is a number. For Ising spins, this number is equal to 1. And the transition temperature in this technique is found as a point where this quantity, which is actually relaxation time, diverges. Beta increases with this inverse temperature, it increases, and we come to a point where of this divergence. So gamma minus 1 diverges as just a linear function of t over Tc minus 1. Okay, this is what I already said, written here. Now, we can just solve close to TC, and for low frequencies, we can find explicitly dependence of green function of omega. So we write it like this. This small j is small with respect to 1, which allows you to rewrite this equation for the green function in the form of just quadratic equation. Quadratic equation with solution in this form. And then we can Fourier transform it, and to get a quite simple expression. Response function decays exponentially with some correlation time t0, which scales like tau in power -2. Tau is a proximity to the critical temperature. And then it also has a power law here. It is time in power 3/2. Good. Now we need to check the assumption about the term with self-energy, which we don't know what it is, but the only thing we need to know is that this term is finite.
What is this new gamma? Is it really?
What I calculated. Look here. I have this equation. What I made is that I say, let us treat this additional term as some constant. We will check that it is indeed constant in the limit of low frequency. If it is so, then we can consider it like some renormalization of this bare kinetic coefficient. Yes, so we will find our result not exactly, but up to some numerical coefficient, which does not depend on proximity to critical temperature. This is important. That what we are looking for is a dependence on temperature and on frequency close to critical point. Before this self-energy estimate, let me emphasize the following point. T0, which scales as tau in power -2, is the maximal relaxation time. It stays here in the exponent. But our response function is not purely exponential. It contains also power law prefactor here. Therefore, we can also define another reasonable quantity, which is here. It is just the average time which is averaged with response function, like here. And this time will have different scaling. It will also grow, but only as a -1 power of temperature. It is the presence of two different critical times is due to existence of the whole spectrum of this relaxation time. I mean, it would be just single time if I would not have here a prefactor. But it is here. So there is a average relaxation rate, and there is a minimal relaxation rate or a maximal relaxation time. Yes, it represents us with fact that our dynamics of our system is characterized by a spectrum of relaxation times. It has some cutoff with this T naught, but there are many other relaxation times which are shorter than this T naught. And averaging over this spectrum gives us this prefactor. The same feature will be seen in even much more important way in a short-range system, which we will discuss soon. Now about self-energy. So we don't need to calculate it really. What we need is to consider this derivative of self-energy over frequency. This derivative is given by this double integral. You will see it if you draw a diagram with nonlinear vertices. Now, according to the solution which we get, correlation function in Fourier space behaves like this, even at the transition temperature, when T naught goes to infinity. And response function is omega in power 1/2. So when you estimate this powers here, and you see that there is no divergence. This integral is infrared finite. So that's all. It is some constant. Okay, this is what we learned about Sherrington-Kirkpatrick model above TC. Now let us look how.
Sorry.
Yes.
To how I
Yes.
this expression that you said about the diagrams, like more specifically, more precisely, how they get it.
This. Okay. We have here this third order term, right? So let us write self-energy sigma of omega will be proportional to the integral like this. This full line is a correlation function, and wavy line is a response function. This is what you will find if you consider diagrammatic expansion for this G with such a vertex. Now, this is what is written here, C, and J. And derivative is because I need to differentiate here. So this is what you will have. Now let's come closer to reality. First, this Monte Carlo experiment on short-range three-dimensional spin glass. Here, the model is on a cubic lattice, coupling with J are plus minus 1, as far as I remember. It was not Gaussian distributed, but not so important. Plus minus 1, and then this Monte Carlo simulation studied just correlation function of spins. Correlation time start to grow below about 4, and when it grows faster and faster, and it grows, you see, up to 8 orders of magnitude. In more details, how it looks like. On these upper plots, it is just the same data, but in a correlation function itself or a logarithm of correlation function is shown. Very important point is that, contrary to what I told you about Sherrington-Kirkpatrick model, here relaxation is not an exponential plus power law prefactor, but instead here we see time in some power beta which is smaller than 1. This fact is shown in a very explicit way on the left plot. What is shown here is a combination, time divided by logarithm of correlation function, plotted as a function of time on the logarithmic log scale. So here on this axis, it is logarithm of this combination, and here it is time in log scale. If q would decay exponentially as simple exponent, then this combination would be constant. But it is not constant at all. It shows some continuous growth, and the slope of this growth allows to determine what is beta. And here you see how this beta depends on temperature. It is 1 above some 4.5 or something like this, which is, by the way, a temperature of transition to ferromagnet state if it would be not spin glass, but all couplings would be ferromagnet. This is a ferromagnet transition temperature on cubic lattice. By some mystery, the spin glass knows something about this point. Below this temperature, beta decreases, and approaches something close to 1/3. Why 1/3? God knows. Experimental fact. I will discuss this point later. But from this very large scale experiment, by the way, here, largest size is 64 cube. And remember, it was done 40 years ago. I don't know how, but it is, I think it's best result still now.
So one question, and this t over logarithm of qt, where is t like if there is just exponential behavior, but if I consider also the power not t to the x there, I may have attained the divergence, but beta can be equal to 1.
I did not understood. What you propose?
My question is why here we are comparing just with the exponential, and that there is also the power law below at the denominator. If I consider it, I will get the divergence.
But look, power law contribute quite not much to this all this evolution. You see, this q changes by orders of magnitude. I mean that the major contribution to the variation of this q with time comes from this exponential. T with x also was extracted by accurate fit. It is rather small, this exponent here. Actually, this exponent x is about 1/2 at high temperature, and it decreases to almost zero close to critical point. So the critical point, which determined as a point of divergence of relaxation time, was found like this, and the critical exponents, with exponents nu, correlation length exponent, and the correlation time exponent is a product of nu by z. And it is, see, this product is something like, what, about 8. Now, this is for maximal relaxation time. As I mentioned before, in this situation, we could also define average one. The average one, it will also diverge, but with a smaller exponent. So, comparison between mean field and three-dimensional spin glass. Stretch exponential relaxation instead of simple exponential, completely different exponent z nu, and also different power law exponent. Now let us look for different example of Monte Carlo simulation. This was a result of some exercises just for fun of one of our students a few years ago. He simulated two-dimensional array of, I think, about 100 by 100 spins, two-dimensional. It is known for many years that in two-dimensional Ising spin glass does not have a glass transition at some non-zero temperature. The singularity in thermodynamics is only at t equals 0. If I remember correctly, relaxation time was found something like t to minus 4, something like this, in two dimensions. But interesting point is that in this two-dimensional problem, what Vlad found is also stretch exponential. This is with decreasing temperature, T, 1.25, 0.9, 0.6. It is not well seen, but here the largest time scale is 1400s. Here it is 60,000. Here it is 3 millions Monte Carlo step per spin. And it is always stretch exponential with exponent decreasing with time, with temperature. And at lowest temperature which he could simulate, it is again 1/3. Although we do not expect even a critical point into dimensions. So this 1/3 seems to be something rather universal, more universal than just existence of finite temperature glass transition. Now let's come to real experiments. Here, what is shown is spin correlation function, is function of time in a very broad range. Here it is, well, this is time scale in seconds, and several orders of magnitude. Again, it is not exponential, it is close to stretch exponential with beta parameter 1/3 or 0.4, something like this. Also another type of experiment where this is a measurement of critical dynamic scaling in a huge frequency range. You see, from -10 to -2 to 10 to 5 Hertz. With two different techniques. At high frequency, it was measured by Faraday rotation method, and at low frequency by squid magnetometer. And all this data shows a critical scaling, well, similar to this Monte Carlo results of Feigel'man. Not exactly, but similar. Now, let us try to discuss the origin of this strange exponent. Here, there is no really developed theory, but there is an interesting idea developed by Ian Campbell long ago in the papers which I mentioned here. He proposed to consider a model which on first sight looks rather different from our original spin glass, namely, he proposed to consider a random walk on a hypercube. Of course, you can present a configuration state of a spin glass in terms of hypercube with dimension of number of spins. Then each flip of a spin is a move along one of edges of this hypercube. Now, his idea was the following. Let us simulate the whole energy relief of our spin glass in a very crude way. We just say that some fraction of the whole configuration space is forbidden because of large energy barriers. So we take this hypercube of large dimension, and when some fraction of these corners of a hypercube will be deleted from our dynamics. So it will be not an original hypercube, but hypercube with some fraction of corners where we can go, and other fraction are eliminated from dynamics. And since it is a hypercube, we can define the quantity like this. Xi is goes over dimension of hypercube. X is a coordinate along the corresponding edge with time. So we calculate this r squared of t. And then let us look how this mean square displacement will approach its infinite time limit.
So Misha, the links are between the vertices. Sorry.
Between vertices of a hypercube.
Okay, so they just differ by single speed.
Mm-hmm.
Speed clip is very differential,
I-
right? Time of fluctuation.
Yes, of course. But here we just forgot about original spin glass. We simply consider the model of this diffusion on a hypercube with some fraction of corners eliminated. Forbidden, just.
So if you eliminate some corners from this hypercube, we are reducing the number of spins.
No,
We
no.
are
You already forgot about spins. No more spins. You consider diffusion over this hypercube.
Yeah, but what does it do is not removing the some vertices from this hypercube, but just throwing in the trash some configuration.
Yes. What hypercube? You say that here, at this point, I never come.
Okay.
All moves which would lead to this point are forbidden. It is not directly related to cluster. It is just not so evident. But the model is like this. It looks very artificial. But strange thing is that here you can simulate this dynamics for different concentration of available fraction of available corners of hypercube. When you decrease this fraction, dynamics becomes more and more slow. And there is a percolation threshold for this dynamics. When you approach this percolation threshold, what you see is this magical number.
Is this related to, I mean, you're essentially studying diffusion on some network,
Yes.
right? So you can study the spectral properties of the Laplacian of this network. So this 1/3 is related to those spectral properties?
Probably yes. There is even one paper, I will show it in a moment, which claim that they understand why this exponent is 1/3 at percolation. I tried to understand this paper, but was not successful. But maybe it is correct, and I just did not try long enough. This is again the results of this simulation on a hypercube. You see, what we consider is the approach of this r squared as function of time, how it approaches the asymptotics. And this approach is described by stretch exponential. At the same time, relaxation rate, of course, or here it is relaxation time, it shows a critical enhancement when you approach the same percolation threshold. Now, I think that there is a theoretical model which could describe this phenomenon and this one-third. But I don't know any attempt to solve it, I mean, for dynamics. Namely, if we compare mean field model, which I discussed in the beginning, with short-range models, there are two important differences. One is that in mean field model, you don't have fluctuations, dynamic fluctuations. For example, this collective field C or Q was just single field. We don't need to consider fluctuations between different parts in the system as it would be in a local system. This is one thing. Another thing is that you don't have also statistical fluctuations. And these two differences, I think, may have different influence. So my idea is that you can consider a model which is intermediate between mean field and real short-range system. Namely, you can say that coupling Jij does not have special structure in real space in 3D. But still, it is a matrix which is sparse. So each side is coupled to small number of other sides. For a cubic lattice, each one is coupled to 6 neighbors. Now imagine that you formulate a model where each side is coupled to 6 neighbors, 6 other spins, but they are not necessarily in the local surrounding, but randomly everywhere. This is a sparse matrix. It is definitely much simpler than a real short-range interaction model. But it is considerably more difficult than Shreve-Kirkpatrick, of course.
It's a model of a network.
Yes. Yes, it is a network with low coordination number. This model was studied in terms of statistical mechanics, for example, by Cantor and Sampolinsky in quite details, and there are some other papers. But it was solved for equilibrium statistical mechanics. I don't know if it was any study of dynamics, like what we need here, to find this correlation functions on the approach of to TC. I suspect that it will show the same 1/3 exponent. And the simplest way is to check such a sparse model numerically. Actually, this is what I was hoping Vlad Temkin would do, but he started from two-dimensional model and then everything rolls away. And he is happy to be a PhD student in California, working on something different. This is, I think, quite interesting model, waiting for somebody to try to solve it. And so this is the end for now. Yes, the paper which I mentioned, Alexander and Orbach, yes, they somehow, they stated that they derive this 1/3 but it is worth to study how they did it.
I have a question. Well, first of all, when you study dynamics here, you decide to, you have a specific type of dynamics. You consider spin flips and not, for example, pair flips like Kawasaki dynamics. So would it change something if I would change the type of process?
For classical system close to critical point, we would say general belief is that it will be no any difference, that microscopic details are not important.
So second question, about this model of diffusion. So here you erase certain configurations. What about erasing certain processes? So erasing links and not vertices.
I don't know. I suspect that it might be something similar in the result, but I don't know if anyone tried.
I have a question.
Yes.
You told about the spectrum of different relaxation times. And what I wanted to ask you is, does that have anything to do with the interplay between parallel and hierarchical dynamics that you mentioned in the first lecture?
No, I don't think so, because you can get the same spectrum of relaxation times both in the model of parallel dynamics and in the model of hierarchical dynamics. This is the whole point, that when you consider simple correlation function like of two spins, there is no way to distinguish between these two types of dynamics. You can get the same spectrum of relaxation rates in one way and another way. What you need to distinguish, and what was the really discovery of this Mike Weissman and his colleagues, is that you can distinguish it if you study second noise or a correlation function of four spins. They provide some very non-trivial analysis of these four spin correlation functions. And from this quantity, you can decide if it was parallel or a hierarchical.
Very good. So next lecture is at 1.